For more than 100 years, the speed of light wasn't just a number. It was a sentence, a hard boundary written into the equations that define reality itself.
Technically, you cannot go faster than the speed of light, but space can travel faster than the speed of light.
No matter how advanced our engines became, no matter how clever our fuel systems were, anything with mass was forbidden from ever reaching it. As an object accelerated, its energy demand climbed toward infinity, turning light speed into an asymptote humanity could chase but never touch. That limit shaped our entire vision of the future. But hidden inside Einstein's own work was a quiet exception that most people overlooked. Nothing can move through space faster than light, but space itself has no such restriction. The universe had already demonstrated this during cosmic inflation, when space-time expanded faster than light without breaking a single physical law. Black holes do it locally, stretching and folding distance so violently that direction and separation lose their meaning near an event horizon. NASA's breakthrough began when engineers stopped trying to outrun light and instead asked a more dangerous question. What if motion wasn't the problem at all? What if distance itself was negotiable? This wasn't about building a faster rocket. It was about changing the shape of the path. Inside a secured facility, far from public view, NASA researchers focused on manipulating space-time curvature on a small, controlled scale. And when the first test succeeded, it didn't look like speed, it looked like absence. The test craft never accelerated. That was the part that unsettled everyone watching. It sat suspended inside a carefully controlled field, instruments stable, internal clocks ticking normally. When the system activated, there was no thrust, no vibration, no thermal spike. From inside the craft, nothing happened at all. From outside, space-time did. The region in front of the craft compressed. The region behind it expanded. A localized warp bubble formed, separating the craft from the surrounding geometry. Inside that bubble, space-time remained flat and ordinary. Outside, distance itself was briefly rearranged. Then the bubble released. The craft vanished from its original coordinates and reappeared at a second location, exactly where the equations predicted. It hadn't traveled through the intervening space. That space had ceased to exist in the same way for a moment. Engineers ran the test again and again, 17 times in one night. Each result identical. No violation of relativity, no paradoxes, no temporal instability. The realization hit slowly, then all at once. Velocity no longer mattered. Acceleration was irrelevant. The light speed barrier hadn't been challenged, it had been bypassed. NASA hadn't created something that moves faster than light. They had created something that makes light speed irrelevant by rewriting the geometry it travels through. The idea itself wasn't new. In fact, it had been sitting in plain sight for decades. In 1994, physicist Miguel Alcubierre published a set of equations that described a strange but mathematically valid solution to Einstein's field equations. His model showed how space-time could be warped into a bubble, compressed in front and expanded behind, allowing effective faster-than-light travel without violating relativity. On paper, it worked beautifully. In reality, it was dismissed almost immediately. The Alcubierre drive required exotic matter with negative energy density, not just trace amounts, but quantities comparable to planetary masses. Energy demands so absurd they rendered the concept effectively useless. The equations were filed away as elegant curiosities, interesting mathematics, impossible engineering. For nearly 30 years, that's where the idea stayed. NASA didn't ignore it, they obsessed over it. The breakthrough came when engineers realized the equations weren't wrong, the assumptions were. The warp bubble didn't need to span vast distances. It didn't need to be powerful enough to fold light years of space. It needed to be stable, localized, and precisely controlled. Instead of generating negative energy directly, NASA's team turned to the quantum vacuum itself. Empty space is not empty. It is alive with fluctuations, particles forming and annihilating constantly. Normally, these effects average out to zero, but not if you control them. By manipulating quantum vacuum fluctuations with extreme precision, the team learned how to create regions of effective negative energy density without violating conservation laws. That shift changed everything. The impossible energy requirements collapsed from planetary scales to laboratory scales. The Alcubierre drive stopped being a fantasy and became an engineering problem. And engineering problems can be solved. The first full test took place in a facility most people were never meant to know existed. It was early morning. The test craft was small, barely larger than a refrigerator, suspended inside a magnetic containment system.
The field generators came online slowly, shaping the geometry exactly as the simulations demanded. No acceleration curve appeared, no motion registered. Then, the craft was gone. Instruments confirmed what human intuition struggled to accept. The craft still existed. Same mass, same internal state. It had simply stopped occupying its original position and started occupying another one, 100 meters away. No time delay could be measured. The room froze. The engineers reran the test. Then, again, 17 times before sunrise. Each time, the same result. Stable warp bubble formation, controlled space-time displacement, clean reappearance, no shock waves, no radiation spikes beyond predicted boundary effects, no damage to the craft or the chamber. For the first time in human history, space-time had been manipulated deliberately, locally, and reversibly. Later, insiders would quietly admit that several people in the room sat down on the floor afterward, not from exhaustion, from the weight of understanding what had just happened. This wasn't propulsion, this was architecture. Space hadn't been crossed, it had been rearranged. Creating a warp bubble was only half the problem. Keeping it alive was the real challenge. Space-time does not like being reshaped. Even the smallest imbalance in curvature can cascade instantly, collapsing the bubble or creating uncontrolled distortions. Early tests failed because the system couldn't react fast enough. Human operators were useless at this scale. By the time a fluctuation was visible, the geometry had already unraveled. NASA's solution was to remove intuition entirely. At the core of the system sat an autonomous regulator, an AI designed for a single task: maintain space-time stability in real time. It monitored quantum field states, curvature gradients, energy density, and boundary symmetry simultaneously, making thousands of corrections every second. Constant micro-adjustments that kept the bubble balanced on the edge of collapse without ever tipping over. This regulator became the difference between theory and repeatability. With it, the warp bubble could be sustained long enough to matter. Without it, the geometry fell apart almost instantly. Engineers described the process as trying to balance a knife on its edge while the knife itself was made of mathematics. Inside the bubble, everything remained calm. No acceleration, no inertial stress, no relativistic effects. Time flowed normally. Outside, space-time flexed, curved, and released, leaving behind a new configuration of distance. For the first time, engineers weren't just observing physics, they were actively negotiating with it. And physics was cooperating. The most unsettling realization didn't come from the engineers, it came from the theorists. Once the system proved stable, it became clear that velocity was no longer the meaningful metric. The craft inside the bubble wasn't moving faster than light. In fact, it wasn't moving at all relative to its local space-time. From its own perspective, it was at rest. What changed was the definition of separation. Distance, long treated as a fixed quantity, became adjustable. Compress space here, expand it there, release, arrival. This preserved every rule Einstein ever wrote. Nothing with mass exceeded the speed of light. Causality remained intact. Time dilation never appeared inside the bubble. Relativity wasn't broken. It was bypassed using its own permissions. That distinction is why physicists reacted with unease rather than celebration. If distance can be reshaped, then remoteness is no longer absolute. Stars are not far away. They are simply separated by geometry that can, in principle, be engineered. Lightspeed had never been the real barrier. Geometry was, and geometry had just become a tool. NASA hadn't built a faster engine. They had removed distance from the equation entirely. Communication delays, travel time, and strategic separation between worlds all became negotiable variables instead of hard limits. The universe didn't shrink, our assumptions did. The implications became impossible to ignore almost immediately. Once distance stopped behaving like a fixed barrier, every map humanity had ever drawn of the universe became obsolete. Proxima Centauri, 4.2 light-years away, had always been framed as unreachable within a human lifetime. Even optimistic fusion concepts pushed timelines into tens of thousands of years. With controlled space-time warping, those numbers collapsed. NASA engineers began running simulations not in years or decades, but in warp cycles. How many controlled compressions and expansions of space-time would be required to bridge the gap? The answer wasn't centuries, it wasn't even decades, it was shockingly manageable. Depending on field geometry and stability margins, a probe could reach Proxima Centauri in years, possibly months. That realization reframed everything. Mars was no longer a destination, it was a training ground. The outer solar system stopped being remote and became local space. The Kuiper Belt became a neighborhood rather than an edge. Interstellar exploration was no longer theoretical. It became logistical. And logistics can be solved. Quietly, mission architectures were rewritten. Interstellar probes were no longer designed as generational efforts. They became missions with return dates. Data wasn't something future civilizations would receive, it was something current scientists could expect to analyze. For the first time, humanity wasn't imagining life among the stars, it was scheduling it. As the technical implications unfolded, a deeper unease set in. Warp bubbles don't just move objects, they disturb space-time itself. Each activation creates ripples, tiny distortions that propagate outward before fading. Individually, they're insignificant, but physics doesn't forget patterns easily. Inside NASA, a different kind of meeting began to happen. Physicists, ethicists, and philosophers were brought into the same rooms. The real question was what repeated manipulation of space-time might do over long periods. What happens when thousands of warp bubbles are created, then millions? Could space-time accumulate stress? Could distortions overlap in unpredictable ways? Could reality itself develop something like fatigue? No one had answers. One theoretical model suggested space-time might remember curvature changes, accumulating minute scars that could alter local geometry permanently. Another dismissed the idea as paranoia, arguing the universe had survived far more violent distortions naturally. But no one could prove either case. That uncertainty changed the tone of everything. This was no longer just engineering, it was stewardship. Humanity had gained the ability to reshape the fabric of reality itself, even if only locally and briefly. And with that ability came responsibility no civilization had ever carried before. The technology worked. That was no longer in doubt. What it meant was the part no equation could solve. If you like this video, please give it a thumbs up, and like always, we'll see you next time.